So time for the next lecture. We are very pleased to have Christoph Skinner giving us this talk. I forget the title, so I will let Chris tell his title and begin the lecture. Thank you, Chris, for joining online to be able to give this lecture. We appreciate this.
Thank you. I'd like to thank the organizers for the invitation, and I'm sorry I wasn't able to be there in purpose, but I'm very, very happy to give this lecture. I'm going to try to share my screen here. I had something set up, but all right, here we go. Is this what gets seen here? How is this?
Yeah, looks good. Looks good.
Okay. All right. This is the first of a series of talks where Marco Antonio Sangiovanni Vincentelli and I will describe how we've been able to construct some new examples of Euler systems and maybe give a relatively new framework, perhaps, for thinking about these constructions. So we've titled the series Degenerate Automorphic Forms in Euler Systems. The degenerate means that the Euler systems arise from looking at classes in cohomology that arise from maybe automorphic forms, so these that are very simple, like Eisenstein series or theta series or something like that. But before I get into the actual construction, I'd like to sort of review a little bit about Euler systems themselves. And so one of the fundamental problems in algebraic number theory is the relation between special values of L functions, like Dirichlet L functions or L functions of elliptic curves, and the orders of things like class groups or Tate-Schaffer-Ravitch groups, or more generally Selmer groups. We have a vast array of conjectures that suggest what those relationships ought to be. There's the Birch-Swinnerton-Dyer conjecture, the Bloch-Kato conjectures, the Deligne-Beilinson conjectures, et cetera. And of course, the problem is, how do you turn conjectures into proofs? And one of the tools that's been very successful for these problems has been Euler systems, which seem to mediate between both sides, at least in the best of worlds. On the one side, the relationship between Euler systems and orders of Selmer groups comes from Colli-Vaughan's method, which makes use of global and local duality and allows us to, and very generally, to deduce the existence of annihilators or upper bounds on the orders of Selmer groups. And on the other hand, there's the theory of explicit reciprocity laws, which is closely connected to p-adic Hodge theory, which relates the Euler systems to special values of L functions. That relation generally goes through p-adic L functions. I want to say, before I talk about a new construction of Euler systems, I want to say something about these arrows. So I'm going to spend a little time on these. All right, and in fact, Mazur and Rubin in particular emphasized that arrow between Euler systems and orders of Selmer groups should actually have a stop along the way in something called Colli-Vaughan systems. So the argument of Colli-Vaughan using duality takes these Colli-Vaughan systems and produces the bounds on the orders of Selmer groups. And then to get these Colli-Vaughan systems, there's a second procedure called the Colli-Vaughan derivative. And I want to emphasize or spend a little time on these two steps, because they emphasize or illustrate, I think, some of the challenges in producing Euler systems and Colli-Vaughan bounding Selmer groups. All right, so the idea behind bounding Selmer groups, I'll try to explain this. So we have some finite Galois module. So maybe for simplicity, I'll assume that it's a p power order. So it has an action of Zp. And it has a module for the Galois group of some number field F. And then we give ourselves a collection of subgroups of the local cohomology groups of this module. So these are local conditions. So the most important local condition might be that we look at the classes that are unramified at that prime. And once given the collection of local conditions, we can form the corresponding Selmer group. It's a subgroup of the full Galois cohomology group. So sometimes this collection F is called a Selmer structure in the literature. And so in general, H1 or F of M, so the first Galois cohomology group of M is an infinite thing. And so we've cut it down by imposing these local conditions at all the primes, in particular, the condition that it be unramified at all but finitely many primes cuts down the size of this group considerably. And it's finite, and we can ask, what is the size of this? I'll have some examples of such things as we go along, but let me start with just this general setup. So our goal is to bound the size of this, and this is exactly where Galois duality enters. So there's a dual module. So we had our module M, which was a finite ZP module. We can look at the homomorphisms from M into all the pth power roots of unity. So this will carry the natural kind of dual Galois structure. There's a Galois action on the roots of unity, and there's the Galois action on M, and we're taking the dual of M there. There's a natural dual collection of local conditions where you just look at the local condition F sub V star, that's the annihilator of the local condition F of V under local Tate duality. So there's a perfect duality between the local cohomology groups of these two modules. And so we can define its module, and we get a corresponding dual Selmer group. All right, so we're handed one Selmer group with these local conditions F, and we have naturally a dual Selmer group for the dual module. And the idea is to exploit the relation between these that comes from global duality. So here's the main idea for bounding Selmer groups. So the module that we're interested in is the one that's in the middle of this top line. And we choose maybe a finite collection of primes of lambda, where our local conditions, say, are unramified for simplicity. And we can look at the restriction map to the local cohomology groups at those primes. That's what I'll call this map alpha in the top here. And don't worry too much about the kernel. So the kernel is also given by some collection of local conditions, but those local conditions are now that we're zero at those finite collections of primes lambda. There's a corresponding sequence for the dual Selmer group, but now the dual Selmer group is not in the middle, it's the kernel. We relax the conditions at the primes in S. We allow them to be ramified. So we allow them actually to be anything at lambda and S. And then we look at the restriction of that group into the collection, into the primes at lambda. But now we're just interested in their images when we restrict to inertia. Why are we interested in when we're restricted to inertia? Well, we restricted the classes, the group that we were interested in, to the unramified subgroups. And so the dual of the unramified subgroups under local duality turns out can be identified with the inertia or the ramified classes on the dual side. So locally on the right of these two exact sequences, we have a product of local groups that are in perfect duality with each other. And what global duality tells us is that the image of the global classes, the image of alpha and the image of beta in these two maps, are mutual annihilators under this perfect duality. And so in principle, at least, you can determine the size of one image by knowing something about the other image. And very ideally, if the collection of S could have been chosen so that alpha was an injective map, so that we would use the local classes to capture all the global classes of interest, then the size of the Selmer group of interest, the Selmer group of M, given our local conditions F, can be expressed as the index of the image of the relaxed Selmer group for the dual. And by relaxed, I mean that at the classes in S, we allow anything to go. So this is the image of beta inside these local classes. So this final formula tells us that to bound the Selmer group of M, the Selmer group that we were originally interested in, what we would like to do is produce classes for the dual module that are ramified, and ramified in a way that we can understand how ramified they are. We want to understand actually the size of that image of beta. So we have a challenge here. To bound the size of the Selmer group, we need to produce ramified classes. That's basically the method of Kolyvagin. He bounds the Selmer group in terms of ramified classes, and particularly given a nice collection of ramified classes. Let's see this in work. Let's look at an example where the number field is Q adjoin the pth roots of unity for a prime P. M is just going to be Z mod P to the MZ. The exponent M doesn't matter. And G of F, the Galois group, is going to be acting trivially. So this is just the trivial module. I'm going to take my local conditions to be everywhere unramified. Because it's the trivial module, then we know that the first Galois cohomology is just the homomorphisms of the Galois group to M. The condition of being unramified everywhere means that this is going to factor through the Galois group of the maximal unramified abelian extension of F. And by class field theory, this is identified with the class group of F. So we're looking at the homomorphisms from the class group of F to Z mod P to the MZ. Great. So we're trying to capture the P part of the class group. And so let's choose a prime L that splits completely in F over Q and take our set S to be just the divisors of L. So the primes lambda of F that divide L. And we look at our localization sequence that we had before. So we take this map alpha, we'll restrict to the unramified classes at each of the primes lambda and S. Those local groups can be identified with Z mod P to the MZ itself in this case. And the identification is made very precisely. We take one of our homomorphisms, call it psi, and we're just mapping it to the value of psi on a Frobenius at lambda. And by class field theory, that Frobenius at lambda is just the class, which I've denoted by the brackets lambda. So it's the class of lambda in the class group. So it's just the image of certain elements of the class group under our homomorphism psi. And maybe because lambda is running over, well, all the primes, well, since L splits completely, we can easily see that we can identify this local target as a rank 1 module over the group algebra. That's also not so important. The dual module for M is just then the homomorphisms from Z mod P to the MZ into the roots of unity. That's naturally identified with the P to the mth roots of unity. And so we can write down the sequence that we had before. We get something that looks very similar. Now we're restricting to inertia groups, but there's these are tamely ramified modules, and so it factors through the homomorphisms from tame inertia and things. And so it can be very explicitly described. The description is very nice once we sort of recast everything in terms of Kummer theory. So Kummer theory describes the H1 of F of mu P M as F cross modulo F, the P to the nth powers of F cross. So that left-hand inclusion is the inclusion that comes from Kummer theory. So if we didn't have the local conditions F star of S there, that would actually be an equality. And then if we take an element X in F cross and its image under these identifications where it is in ramified, we can see how ramified it is by just looking at the valuation of X at lambda. And we can, in some cases, and this is one of the cases, actually just write down some ramified classes. So in the theory of cyclotomic fields, there's a well-known theorem, often called Stickelberger's theorem, which produces an annihilator of the class group of a cyclotomic field. And what it does is it starts with a Gauss sum. It writes down a particularly nice Gauss sum. And in that case, that Gauss sum, which is for characters modulo L, gives us an element in F for the choice of L and the choice of the Gauss sum. That wouldn't be true in general, but it is in this case. And then you analyze the prime factorization of this Gauss sum using the very explicit definition of the Gauss sum. And you discover that the image under this map is actually the generator of the Stickelberger ideal. So it's a particular element. And then the duality tells us then that the Stickelberger ideal or the Stickelberger element annihilates the class group. So this is recast that Stickelberger theorem and its proof in the context or in this sort of picture of Euler systems or Kolyvagin's argument. And so it's an example of where we can write down an element and analyze how ramified it is. But in general, this is a very difficult problem. We're much better at saying that things are unramified, right? So if a variety has good reduction, then its cohomology classes, or its étale cohomology is unramified. If an abelian variety has good reduction, then its Tate module is unramified. It's much harder to sort of go the other way in general, to say that something is actually ramified. We can at least say that if the cohomology is going to be, the étale cohomology is going to be ramified, then we need to have some singularities or something like that. But that may not be sufficient, or at least proving that it's sufficient can be difficult. So we're much better at producing or saying when things are unramified. But what we want to do in this setting is produce ramified things. All right, so this explanation of the role of duality has been all about coming from Kolyvagin systems, which are collections of ramified classes and bounding orders of Selmer groups. But we actually need to find these ramified classes, I said, and we need to do so given that we're much better at proving things are unramified. How do we do this? So the idea of Euler systems, which is where this problem is hopefully resolved, is the following. Well, let's say we have a p-adic Galois representation. So now we have a finite dimensional representation V with coefficients, say, in some finite extension of QP. And we have the Galois group of a number field F acting continuously on V and L linearly. Because of the continuity of that action, we can fix a Galois stable O lattice T inside V, O being the ring of integers of L. L is not going to be important, neither will O. You can just think of QP and ZP if you like. Then an Euler system is a collection of classes, Z sub m, classes in the Galois cohomology of T, where the field is varying. So the field F brackets M, this is supposed to be a ray class field of conductor M. So M is some modulus for the number field, and f of M is some ray class extension of f. So it's an abelian extension of f. We are allowing ramification in these abelian extensions by taking arbitrary moduli. But in general, these classes are probably going to be unramified. Certainly in practice, they'll be unramified. So we're looking at unramified classes, but they don't live over f. They live over a ramified extension of f. And then the Kolyvagin derivative. So Kolyvagin introduced a method by which we can take these classes, at least if they satisfy some close relations, and produce ramified classes over the ground field f. So we take these classes z of m, which are only defined over some finite extension of f, and the Kolyvagin derivative produces a class that's ramified, possibly, but it's over f, but only taking values in some finite quotient of t. So t mod here, pi to the n t, where pi is a uniformizer of O. So again, we're back into the context of a finite ZP module. This works when the classes comprising the Euler system satisfy certain norm relations. There's compatibilities amongst them when you add primes to the modulus. So if I look at the modulus m times lambda for some prime lambda of f, so this class lives over the ring class or the ray class field of m lambda, I can look at the co-restriction of that class, and I can ask to compare that class with the class Zm for the modulus M. And one wants a relation where some compatibility. So in practice, we now know what the kinds of relations that we would like for this procedure to work. If lambda already divided the modulus M, then we should be getting just the class for M on the nose. But if we're actually introducing extra ramification into the field, so lambda didn't divide M, then we don't quite get the class Z of M, but we get a polynomial in the Frobenius of lambda acting on that class. So we get that class, the image of that class under the action of a polynomial in the Frobenius of lambda. And that polynomial, well, there's actually quite a bit of flexibility in what this polynomial can be in practice, but in general, it should look something like the polynomial that gives you the Euler factor for the Galois representation or the L function V, for the L function of V. And that's actually the origin of the name Euler systems. These look like these polynomials that play such an important role in passing from Euler systems to Kolyvagin systems. Look like the Euler factors of an L function. All right, so this is the crude idea of Euler systems, is to take unramified classes over ramified extensions, which satisfy these compatibilities, these norm relations, and produce ramified classes over F. And then global duality takes over and bounds the Selmer group. So that's the theory of Euler systems. The sort of the axiomatic development of Euler systems is very rich and very complete. I was fortunate to see, as a graduate student, to see Carl Rubin deliver a series of lectures at the Institute where he expanded on this, which eventually became his well-referenced book called Euler Systems. Anyway, so now actually, if we go back to that, if you think back to that very first slide, or maybe I've now explained the relation between, say, Euler systems, perhaps, and orders of Selmer groups with this stop along the route for Kolyvagin systems. The other half of the picture was the connections with L values. And this, as I said, goes via what we call explicit reciprocity laws. So if the method of Euler systems makes use of the properties of the classes at the primes different from P by adding these auxiliary primes S into the picture, the explicit reciprocity laws really zero in on what's happening at the primes above P. So the idea is to take one of these classes in our Euler system, Z of M, and localize, say, at a prime above P, and then study what you get. And to use p-adic Hodge theory to describe the situation. So p-adic Hodge theory it relates p-adic Galois representations to linear algebra data that sort of very much mimics the theory of, or reflects the theory of Hodge theory in varieties. And in fact, when everything has a geometric origin, that's exactly what we're seeing. And then this is also a point in which it's important to know where these classes Z that make up the Euler system are coming from, because you can use p-adic Hodge theory to turn it into or express these classes in terms of this sort of linear algebra data. But what have you actually gained? You've only gained something if you can now connect that data to something else. So in the situation where these classes Z of M have some kind of motivic origin, then that linear algebra data really is connected to the de Rham or Hodge theory of something like a variety or a scheme. And then you can try to use additional information there and de Rham pairings and things like this to understand something about your classes. Right. So I'm saying so this is very rough, and I'll give you an example in a minute, and we'll see another example as we go forward. So after this translation into the de Rham world, what happens is that we end up recognizing our classes there. The image of our classes is the special value of an L function via some formula, and this formula will come from some construction or some definition of a p-adic L function. So what happens is that you have the class, you have this translation via p-adic Hodge form theory. This gives you some expression, and just by looking at that expression, you see that it's the same, it's a special value of some other formula that defines a p-adic L function. This is the kind of thing that happens over and over again in this world of special values. If you're sort of more familiar with maybe elliptic curves or something like this, and you think of the Gross-Zagier formula, you have this beautiful formula that expresses the derivative of the L function at 1 in terms of the height of a Heegner point or some point. But how do you get this formula or get this equality? You sort of massage both sides into a formula, and then you stare at those formulas and you see that they're the same thing. All right, let's go back to an example. Well, actually, it's a new example. We're going to take F to be just the number field Q, T to be now the lattice ZP of 1. So it's the Tate twist of ZP. So it's the Tate module of the P power roots of unity. We're interested in cohomology classes. Let's look at a cohomology class over Q adjoins zeta P to the R. P to the R is, so this is P to the rth roots of unity. Kummer theory describes this this cohomology group in terms of the multiplicative group of the field, Q adjoins zeta P to the R. And I'm going to write down just a simple element there, 1 minus zeta P to the R. So this gives me a class in cohomology. I can look at the same Kummer theory locally, so I just take the restriction. And I can take the log of, the p-adic log of my element. I have an action, let's say G to be the Galois group of Q zeta P over Q. Let's take chi to be a primitive even character of this Galois group. which takes values actually in the local field, then if I look at the element zeta ZPDR, which was this from Kummer, came from Kummer theory, I can apply, this is an element of H1 of Q zeta PDR. So there's an action of the Galois group G on the cohomology group, and that's compatible with the action of the Galois group on the elements in Kummer theory. I can formulate or take the expression where I sum over the elements of the Galois group, chi inverse of sigma. So take log p of sigma applied to my element zeta PDR. When I recast that in the description of zeta PDR as ZPDR is 1 minus zeta P to the R, then I get the bottom line. And then I stare at that bottom line, and I realize that that is a formula for the value of the p-adic L function at 1. So I cook up, I have some natural formula in the context of the cohomology locally, and I see just by inspection that it's connected to an L value. This is a very simple case. The p-adic Hodge theory is really this log here. So this is the sort of the fundamental construction in this world. It's the basis for all the other fancy logarithms that you know, the p-adic Bloch-Kato logarithm and things like that, the Perrin-Roos big logarithm. They all come from sort of interpolating or otherwise connecting up with this particular map that I just wrote down. And then it's all about evaluate or writing down expressions or coming up with expressions like this on the left-hand side, and then realizing that they are the special values of formulas for p-adic L functions. Actually, I say that, but one of the things I've always just been dissatisfied with this part of the Euler system sort of machine. And so one of my reasons for looking for other constructions of Euler systems was to try to find ways that were constructions that were more naturally connected to L functions and p-adic L functions. And you'll be able to see by the end of this talk, or maybe by the end of Marco's series, whether or not we've been successful in that. So Euler systems, when they exist, have been very effective for relating values of p-adic L functions to orders of Selmer groups. Orders of Selmer groups, of course, p-adic Galois representations. But when do they exist? It's expected that they should exist very generally. They're a collection of sort of, maybe going back to Perrin-Roos and Kato, and certainly, as I said, sort of developed considerably a sort of a general machine that would apply to Galois apply to Galois representations. A large class of Galois representations, but okay. But what actually is known, and what are some of the open problems? It might be, I'm going to shift into describing a little bit of the history, and then I'm going to describe a new construction. So it might be a good point at which to ask if there were any questions about this rather rapid overview of the method of Euler systems. All right, well, assuming not, then I will move on to saying something about when do Euler systems exist. All right, well, here's a kind of very short history. In the 1980s, we really only knew 2 Euler systems. We knew the Euler system for the Tate module ZP1 and the field Q. This came out of the work of Tian and Kolyvagin, and the cohomology classes of interest arose from Kummer theory via cyclotomic units. We also knew an Euler system for, again, for T being ZP of 1, but now F is the imaginary quadratic field. This was a construction of Rubin, where the cyclotomic units are now enriched to be the elliptic units. Now, there's also the work of Kolyvagin on elliptic curves, but that doesn't quite fit into the framework that I'm talking about. I'll say something more about that in a minute. Then in the 1990s, there was an addition. Kato produced a rather amazing construction of an Euler system for modular forms, or let's specialize to the case of the Tate module of an elliptic curve. So T is now the Tate module, the prime P of an elliptic curve. And the special elements came from modular units. The restriction of cup products, in fact, of taking two modular units, taking their cup product, and that gave us some modular unit and a class on some modular curve. And then he was able to show that from these he could construct an Euler system. And then about 20 years later, well, at least 2 decades, and then if we're counting by decades, 2 decades later, in the early 2010s, Antonio Ley, David Loeffler, and Sarah Tserbas showed that an old construction of Beilinson and Floch could be massaged into an Euler system for the Rankine product of two modular forms. So now T is the tensor product of the Tate module, or of the Galois representations associated to two modular new forms, F and G, say, or possibly the Asay L function of the Hilbert modular form. And they could take a modular unit, which gave a class in the absolute étale cohomology of a modular curve, and then push this forward into either the product of the modular curve or into the Hilbert modular surface, and they got a nice collection of classes that they could show was an Euler system, and for which they could compute the explicit reciprocity law. So I think this was very, very important for a number of reasons. First of all, it's had nice arithmetic applications, but also psychologically, it suggested that the world of Euler systems wasn't completely inaccessible beyond the handful of examples we'd known in the previous century. So in the late 2010s, in collaboration with Loeffler and Tserbas, we constructed a Euler systems for the spin L function, the degree 4 Galois representation of GSP4, the standard representation, so the degree 3 Galois representation for GU21, still by pushing forward modular units. So in the case of GSP4, you would take two modular units on the embedded product of two modular curves, for instance. Similar arguments gave rise to Euler system, or the definition of Euler systems for GSP4 cross GL2 and GSP4 cross GL2 cross GL2. The difficulty here, these constructed are defined classes, improved norm relations. The collaborative efforts did not prove the connection with p-adic L functions, though we did in another paper construct the p-adic L function. And David and Sarah have been very actively pursuing and made some remarkable progress towards producing those explicit reciprocity laws. And that's involved the recent advances in Hida theory that go under the sort of rubric of higher Hida theory. This is not completely comprehensive. Also in the 2010s, Eric Urban was sort of making some very interesting constructions with Eisenstein congruences that led to Euler systems in various settings, among which was the adjoint L function of a modular form. Also, as I said, I haven't said anything about the Euler systems for anticyclotomic extensions, which are those that are more like what Kolyvagin did in his celebrated work for elliptic curves. That's a slightly separate theory. It's closely, well, there's been a lot of progress recently, closely sort of paralleling the work in Euler systems in the sense of Rubin et al. From a few decades ago. There may even be some talks in this workshop or next week where some of this progress is described. But I had to choose my theme and stick to it. All right, so the rest of this talk in this series is going to describe a construction of Euler systems that replaces all these units with classes arising from special automorphic forms. So the problem is, if you look back at all of these examples, Erika's work is the outlier here. All the classes arise from units. We have cyclotomic units, we have elliptic units, modular units, and then modular units in various forms and guises. We need to sort of find some substitute for modular units. Here's the point, which I'm not really emphasizing, is that one should think of or look for some sort of motivic origin for these cohomology classes. And if you're looking for motivic origins, you're really looking for things in K-theory. And now we need to write down classes in K-theory, and we're best writing down classes in K-theory when we just write down units and sort of various symbols constructed from units. But that only seems to get us so far. And so one of the other motivations for me to think about Euler systems was to try to think about ways of constructing Euler systems that didn't rely on these explicit descriptions of motivic cohomology classes. That's not to say that these classes aren't motivic in some sense. It's just that I'm trying to get away with as little bit of information about them as I can. Okay. So, okay, this is a slide that says, okay, I have ignored, as I said, Kolyvagin's Heegner point Euler systems and all subsequent developments of anticyclotomic Euler systems. Anticyclotomics mean here means that those ray class fields Fm are restricted to being ring class extensions of Cm fields, hence the anticyclotomic nomenclature. This subject has seen, as I said, many new results. I am not talking about those in this talk, but I'm certainly happy to answer questions about them. All right. Here is the way I'm going to think about constructing classes that will make up an Euler system. And then we're actually going to do an example. So V is going to be a p-adic Galois representation. We're looking for classes, cohomology classes of V. So Galois cohomology classes. And so if we have a class in H1F of V, this is the class of some extension of GF representations. Actually, it's the extension of the trivial representation by V, or V by the trivial representation. I'm really bad with remembering what the conventions are for extensions. Anyway, it's an exact sequence 0 to V to this extension E of C, and then the quotient is the trivial representation. So L is, again, this finite extension of QP. That's the coefficient field for my Galois representation V. So the isomorphism classes of such GF extensions can be identified with the H1F of V, this Galois cohomology group. So one way to define classes is to look for such extensions. One place to look for such extensions is in the cohomology of varieties, particularly open or varieties or something like them. And then the question is which varieties to look into. Well, I mean, the situations that we're most interested in, the Galois representation V arises from the cohomology of some variety, say an elliptic curve. So V could be the Tate module of the elliptic curve. And then where might you find extensions? Well, one place you could look is then start removing points from your elliptic curve and look at the open variety. and that's supposed to have some kind of mixed Hodge structure. And on the p-adic side, you should see extensions. That's actually hard to analyze, and the way where we're going to look for the extensions is to find the variety that gives rise to the Galois representation V as a subvariety of something else. And then we're going to be excising that subvariety and then looking in the open variety. Okay, but still you have to ask which collections of varieties to look at and stuff like this. And it's still very much an art, not a science. And for me, it's governed by integral representations of L functions. So I take some integral representation of L functions, and I try to think of it as having some kind of geometric reflection, and that tells me which varieties to start looking at. And this is more than just some sort of guide. And it turns out when this works, the explicit reciprocity law connects up exactly with those integral representations. So the connection to L values is going to come also from these integral representations. All right, so let's do an example. And so here's the motivation. The Serre-Katz construction of p-adic L functions for Dirichlet characters comes about by just looking at the constant terms of p-adic families of Eisenstein series. So we can think of this as just taking the values at the cusps of p-adic Eisenstein series. So it's a very simple, if you want to think of it as an integral representation, it's a very simple integral representation. We're integrating over a point. But this leads us to focus on cohomology classes that come from Eisenstein series and cusps. So let me describe now this more explicitly. So let's look at the Eisenstein series. Let's take an integer n. Let's take an even Dirichlet character mod n. Let's call it chi. And we'll construct an Eisenstein series for chi. I'm not assuming that chi is primitive, by the way. And so in fact, the fact that we allow imprimitive characters is very important. So I'm just looking at any Dirichlet character mod n, and I'm going to look at the Eisenstein series of weight 2 associated with chi. Well, a particular Eisenstein weight series associated with chi. Constant term is an L value. And then the Fourier coefficients at the positive integers n are very simple to write down. At n, it's the sum over the divisors of n of chi of d times d. This nice divisor sum, or twisted by the character. The Hecke action this is a Hecke eigenform, and the Hecke action is also very easy to write down. T of L acts as 1 plus chi of LL times C of chi n. It's a holomorphic modular form, and it gives us then a differential, a holomorphic differential on the open modular curve. So E chi of n tau d tau, tau being the variable in the upper half plane. Or I can think of this as a differential on the closed curve, but with logarithmic poles at the cusps, or at least at the infinity cusps. And I'll call this differential omega chi. So the cusps of the modular curve are very explicit. They're identified with the gamma 1 n orbits of points on the rational points on the projective line. And I'm not going to go through these formulas, but there's a collection of points, of cusps, which I'll call the infinity cusps. That's going to be where the point in projective space, if I'm writing in with integer coordinates a and c, n is going to divide the integer c, and the zero cusps are where n divides the entry a. All right. These are not all the cusps, but they're a particularly nice collection of cusps for C1 of it. And all right, so I'm going to take y, I'll decorate it with this infinity to mean I've taken the closed modular curve, but I've removed the cusps at infinity. Why am I removing the cusps at infinity? These are the cusps where my differential or my Eisenstein series has constant terms. Okay, yeah, all right. And then I can look at the class in de Rham cohomology defined by my holomorphic differential, call that C of chi. By the de Rham singular comparison theorem, which is just de Rham theory, I can identify this with the singular cohomology of this non-compact Riemann surface, Y infinity, or which is also an algebraic variety over Q. The first thing that one observes is that this class, which is a priori transcendental and defined over C, actually has gives me a cohomology class, a singular cohomology class with coefficients in Q of chi, where Q of chi is just the extension of Q containing the values of chi. So in some sense, this is a rational class. And in fact, if we look at the class C of n, where we're averaging over all the characters, all the even characters modulo n of these C chi's, we in fact do get a singular cohomology class, which with coefficients in Q. So it's a rational class. How do you prove this? This is the Menin-Drenfeld principle in action. So you look, Eisenstein series, sort of the general theory of Eisenstein series tells us that Eisenstein series are completely controlled by their constant terms. And so in this case, we can look at the constant terms or the reflection of the constant terms for cohomology, which would be the residues and the residue classes over the infinite cusps. And we can see that those are rational. And then we can use the fact that the Hecke operators separate Eisenstein series from cusp forms to then conclude that the Eisenstein classes, the classes coming from Eisenstein series, are rational with coefficients in the fields indicated. And so this is a principle that's been exploited and studied quite a bit by Harder and his school in their study of Eisenstein cohomology, right? But once we have these coefficients or these classes in singular cohomology with rational coefficients, we can also view them as in singular cohomology with p-adic coefficients. And then the singular étale comparison isomorphism says that we can also think of them as being étale cohomology classes. So this is a very sort of, soft way of producing étale cohomology classes. In particular, the class C of n belongs to the étale cohomology of our variety with coefficients in QP. And then we can ask the question, well, how does the Galois group of Q act on these classes? Since it acts on étale cohomology. And we can again use the Menin-Drenfeld principle to answer this question, because once again, we can look at how the Galois group is acting on the residual classes, the classes coming from constant terms where everything's very explicit. And we discovered that the Galois group acts on GQ, acts on by the inverse of the cyclotomic character. Or we can think of, say, the GQ in particular, GQ of adjoining the nth roots of unity acts on C of n by this inverse of the cyclotomic character. That's a consequence of the first observation there. As I said, the proofs of these statements are all the Menin-Drenfeld principle. So we've written down some nice classes in étale cohomology that arise from these simple or degenerate automorphic forms, these Eisenstein series, and we're able to sort of just by using that degeneracy study the rationality of the class and the action of the Galois group on it. And now here is a more difficult fact. The class C of n actually is not just a rational class, but it's in fact an integral étale cohomology class. And this makes use of some p-adic Hodge theory. So certainly the class C of n is coming from the average of the classes C of chi, and the classes C of chi come from these Eisenstein series, E chi. And so we're really looking at the de Rham class coming from the average of these E chi's. And so I'm missing a sum over chi's in that. So it should be 1 over the number of chi's times the sum over the chi's of E chi n. Because of the Fourier coefficients, you can see that this is a very nice Q expansion. Its Q expansion is in fact just integers, so it's in ZP. And the important thing is that these Eisenstein series are P ordinary in the sense that the TP operator is acting by a a unit. I should be assuming probably that P divides N in this case. And so then the TP operator is just acting by 1. All right. And then an argument due to faultings allows us to conclude in this case, and in many, very generally, that because the class is ordinary and because the Q expansions are integral, that that the class C of N, the Étale cohomology class associated with it, is in fact an integral class. So this is true even when a high power of P divides N. So I have to, and I don't have to analyze sort of models of the modular form or anything like this. This is a very soft fact. And okay, so why am I doing this? That gives us an integral cohomology class. But it's actually more convenient to work with not these classes, but their reflections under an Aitken-Lehner involution, which is going to give a class now in an integral, still an integral cohomology class, but now for Y, where Y is not Y infinity, but it's Y, it's the open modular curve where I've removed the cusps at 0. But I'm allowed to keep the cusps at infinity in there, and that's kind of crucial for later on. So I get these classes, which I'll now call eta sub n, that come, but I still know the Galois action. The Aitken-Lehner involution, its action is compatible with Galois, at least if I pass to the nth roots of unity. And so now I have that still have that G of the extension Q adjoin the nth roots of unity acts on this other class eta sub n by the inverse of the cyclotomic character. So now we're at a situation where we can define our Euler system. So as I said, Y is the modular curve where I've removed the cusps at 0. And I'm going to look at a subvariety of Y, which is in fact the cusps at infinity. So I have this curve, this open curve, and then I have a collection of points. And these are all defined over Q. And now I'm going to look at a sequence in Étale cohomology. I'm going to look at relative cohomology. I'm going to look at the cohomology of this open variety Y relative to the closed subvariety W. And so I have as a quotient, I have the cohomology of the variety Y. And as a kernel, I have the image of well, in this case, the H0 of W. And so the Galois representation that, well, maybe I won't worry about Galois representations yet. We'll reinterpret this sequence later. So I'm going to look, now I'm going to do a construction where I pull back from the class of eta n. So I have this class eta of n that sits inside H1 of Y, and it generates a submodule ZP minus 1 because we know what the Galois action is. We look at its inverse image in H1 in the relative cohomology. So that's some Galois module. And then I'm going to push forward by some quotient from the H0 of W, which I haven't quite this right. What I'm really looking at, and I didn't write this quite right, I'm looking at the evaluation. Well, I'd like to evaluate it at the cusp at infinity, but I need my whatever I'm pushing forward to vanish on the image of the H0 of Y itself, which of course is the constant. So it's the diagonal, the embedded constants on the cusps there. And so I need to look at the difference of two cusps. And now I'm realizing I wrote that wrong. But what this is, this map, this left surjection is just the difference of two cusps. And so now this gives me an extension of modules which have Galois actions. They have a GQ mu n action, and they're ZP modules. So it gives me an extension, epsilon E sub n, and I can take the class of this extension in cohomology, and I'll call that Z of n, and that's my candidate for an Euler system, or the collection of these classes is my candidate for an Euler system. So let's review the construction. So we looked at the cohomology of this variety Y. We looked at a class, a very simple class arising in Y from a very simple automorphic form, in this case, an Eisenstein series, and that gave us a very simple Galois submodule. Here we have just ZP of -1. And then we looked at relative cohomology. We just looked at cohomology relative to some subvariety. And then we did a pull back, push forward construction to get an extension. And then we just take the class of that extension. If I had replaced ZP here with ZP of 1, then all that would do, that's just twisting the Galois representations by the take twist 1, then the sub-extension becomes the trivial representation. We're looking at ZP embedded inside there, and the push out would be to ZP of 1, which is in fact the representation that we're getting cohomology classes for. So if you remember what I said, you take some subvariety where the Galois representation that you're interested in shows up, and then you look at a larger variety, in this case W or Y. So we look at W inside Y, and then we do a construction in the cohomology of that larger variety to find our classes. So that's what's happening here. What about norm relations? So we could have made a similar construction. We defined eta of n, but we could also have defined eta of chi for a character chi mod n as the image of C chi under the sort of the Atkin-Lehner involution. There's a Galois action on it, but now the Galois group acts as chi inverse times epsilon to the -1. Remember, the Atkin-Lehner involution isn't quite compatible with the action of the Galois group of Q. I mean, it is if you change your models of your modular curves. So, but anyway, and so it's easy to read off from this how the co-restriction map acts, because we understand how Galois is acting on these classes C of chi. And so it's very easy to see that the co-restriction of the class Z of NL, where I've added L to a new prime L to N, it's a trace, the Galois action. So it ends up being the extension corresponding to the pullback push forward of the sum of the chi's mod. So Z of NL is the sum over the chi's mod NL, and the only ones that survive under the co-restriction map are the ones that came from N in the first place. But they're not, but we haven't gotten back eta of the chi mod N because we're viewing these characters as mod NL. So I'm writing this as the sum over the characters mod N of eta of chi prime, where chi prime is where we view chi as giving us a character mod NL. And so there's the Eisenstein series for chi mod N is not quite the same as the Eisenstein series for chi mod NL. There's been for the chi prime, because there's something that's happening at L, and that's exactly where we're going to see the norm relations. And so if I looked at, in fact, let's see this. So E chi prime tau is actually just E chi of tau minus chi of LL times E of chi L tau. And now if I apply the Atkin-Lehner involution to this or something like this, I just recover a formula that says the class of chi prime is just the pullback of the class of chi under the degeneracy map tau goes to L tau minus a Frobenius action. Where's that Frobenius action coming from? It's comparing this the chi of LL that we've in front of E chi L tau with our understanding of the Galois action on the class. Frobenius L of the pullback to the modular curve of level Ln of eta chi now under the usual degeneracy map, and tau goes to tau. Each of those pullbacks gives the same Galois extension. And so we're just getting 1 minus the Frobenius of L minus 1 times our class. So we're getting some nice polynomial in the Frobenius of L, which is good enough for the weather system argument. What do I mean by good enough? I mean that, to get an weather system, the exact form if you want to fit whatever construction one makes into like this one into the axiomatic treatments in the literature, you almost always have to make some slight modifications of the naturally defined classes. But that's only really to sort of massage into the form of these axiomatic treatments. There's actually, if you go back and you study the Euler systems, there's a lot of flexibility in the definition of what an Euler system is. So this is just noise in the whole program. Right. That gave us, okay, so that, what has this got us? This has got us a collection of classes coming from Eisenstein series, classes for the cohomology of the ZP of 1, varying over abelian extensions of Q that satisfy certain norm relations. That's kind of the Euler system. And we can run the whole Kolyvagin argument with that. But for it to be interesting, we need to connect with p-adic L functions somehow. So we need the explicit reciprocity law. So let me explain the explicit reciprocity law in this context. And what I want to emphasize is that the eventual connection to the p-adic L function is going to come from the Katz-Serre construction of the p-adic L function. We're just going to look at the constant term of a p-adic Eisenstein series. So we looked at constant terms of p-adic Eisenstein series to understand our Euler system. We're going to look at constant terms of p-adic Eisenstein series to sort of see the explicit reciprocity law. So this whole sort of construction of the p-adic L function is kind of reflected in everything we've done. All right, so the explicit reciprocity law, here's an example. Now I'm going to make some simplifying assumptions, so I didn't have to write too many slides. I'm going to take an integer n where p doesn't divide n. I'm going to take a character mod n that's primitive. This is all for simplicity. I'm going to look at the Eisenstein series now, G sub chi, which is a little different from E sub chi. It's the sum, the constant term is 0, and the infinity is 0, and the coefficients are given by the divisor sums, where I'm summing over the divisors of n d times chi inverse evaluated at n over d. So previously I had d times chi of d. So this is actually the Eisenstein series that you would get up to epsilon factor from applying the Atkin-Lehner involution to E of chi. So all this is actually the Eisenstein series you get from that corresponds to the class eta. So if I look at this Eisenstein series, I can look at g chi of q dq over q. So I'm now expressing this as in terms of differentials over q. This gives me then a differential in the modular curve, and so that's defined over q, or hence over qp. So I can think of this as giving me a class in H1 de Rham of the variety y over qp, and I'll call this sort of the p-adic eta chi. So eta chi p-adic. So the idea is to look at this large diagram in the middle. What have we done? We've taken the diagram in étale cohomology, which gave rise to our extension, and we applied the d de Rham functor of p-adic Hodge theory to that extension and to the subquotient that gave us our class. So that's the middle line, just we're applying d de Rham to this étale cohomology. And then the p-adic de Rham étale comparison theorem identifies that sequence now, taking the étale cohomology and applying d de Rham with the corresponding sequence in de Rham cohomology over qp. So now we're just looking at the de Rham cohomology, the relative de Rham cohomology of the variety over qp. So it's exactly, so the top line is exactly the same sequence that we had for étale cohomology, but now for de Rham cohomology. And what we're interested in is studying the subquotient that we constructed by pull back and push forward. But that's now identified with a subquotient of the relative de Rham cohomology. Now, the fact that our classes associated to the Eisenstein series had such nice Galois action means that we can explicitly identify them in all of these settings. And so in fact, the d de Rham of our submodule QP generated by eta sub chi. So the eta sub chi being the differential of the Eisenstein series, or E sub chi, but with the Atkin-Lehner evolution applied, we can see that we have is one-dimensional over QP, and that a generator is eta sub chi tensor a particular element T in the in B de Rham, and in the ring of periods underlying the D de Rham, where the Galois action on T, the local Galois action, is through the cyclotomic character. So that's canceling out the cyclotomic inverse that's acting on eta of chi. But on eta of chi, there was also an action of chi inverse, and so there's a Gauss sum, a division by this tau of chi, the Gauss sum, and so now that's canceling all of the Galois action. And when under these identifications, this actually gets identified in H1 de Rham with the p-adic expression for this differential, with the eta chi p-adic. So one can be very explicit with what's happening. What we want to compute for this explicit reciprocity law was the Bloch-Kato logarithm of this extension E sub chi. And that's also got a very, very concrete expression. Acting on all of these modules is a Frobenius element, phi sub p, the Frobenius of p-adic Hodge theory, because in fact de Rham is potentially semi-stable and everything is over QP, and so we actually have this Frobenius element, and we know how it acts. And so the Bloch-Kato logarithm is really wants to describe this extension. And how would we describe the extension? We would pick a lift of the so particularly wants to describe the bottom row. So we would pick a lift of our generator of the quotient. So we have this one-dimensional quotient with a generator that's just very explicitly. We pick a lift of that generator to the middle. We apply a particular polynomial in Frobenius that annihilates the image of our one-dimensional, so annihilates the one-dimensional line. And so when what we're left with must have come from QP, and what that number is, what that element of QP is exactly what we're trying to compute. That is the Bloch-Kato logarithm of this extension, and we just want to know what is it. We want to see it as a p-adic L function. That's really just kind of describing the extension. And so we do this by passing to the world of p-adic modular forms. So this slide, this first part of the slide is just saying exactly what I said in words before. There's some polynomial in the p-adic Frobenius that's going to annihilate that annihilates our one-dimensional quotient, and so we apply it to our lift. Now here we're in a nice situation that our Eisenstein series G chi, see, it had constant terms that are 0 at the infinity cusps, so it actually gives us a differential that vanishes at W. So we can think of it as defining a class in cohomology, in the relative cohomology already. So that gives us, so we can actually write down a nice lift, and that nice lift is in fact just the Eisenstein series that the image of the Eisenstein series that we were writing down before. Of course, the conditions, the relations that define cohomology will possibly be different. Then we look at this polynomial 1 minus chi of pp. This is coming from the action of Frobenius on the Eisenstein class. This annihilates the class in the cohomology of Y, and what we're interested in is does it or does it not annihilate the class in relative cohomology? And actually, so what is that? So we apply that, and we have something that's in the image of the H0 deram of W, because it's vanishing in the quotient, and we want to know what it is. Can we actually compute this? And we can compute this using p-adic modular forms. So if we restrict from the modular curve to the ordinary locus of the modular curve, and again, this is another place where it's useful that we're working with Y, because now the cusps are ordinary. The cusps of infinity, sorry, are ordinary. And so this picture is nicely reflected still in the ordinary locus. We would have a problem if we had stuck with W being the cusps at 0, and we left Y as Y infinity, because then when we were taking the ordinary locus, we'd been throwing out W to begin with, and we wouldn't, over the ordinary locus, we wouldn't be able to see this kind of relative picture. All right. Now we want to compute this. So we restrict to the ordinary locus, express all of our de Rham cohomology in terms of p-adic modular forms. So what do we want to do? We want to compute a primitive of this differential, and then restrict it to W and evaluate it. Actually, what we want to do is we want to compute a primitive of the differential 1 minus chi p Frobenius of p applied to eta. So 1 minus chi p of p infinity applied to eta of chi is the the Eisenstein series, or the class of the Eisenstein series that has its p critical stabilization, meaning the UP operator is now acting as multiplication by p. The primitive of this, its image under the QDQ operator, is the weight 0 p ordinary Eisenstein series for the character chi inverse. And that has constant terms. And now we evaluate those constant terms. That's what we want to do. So we found the primitive. We restrict to the cusps at infinity. And we take the values, or the difference of values at 2 of the infinity cusps. Well, the value of the weight 0 p ordinary Eisenstein series at the infinite cusp is L1 of chi. And the difference of the 2 cusps, which again I've messed up, is just possibly where we remove an Euler factor. There's some noise in the system, but we have some choice in that R. That doesn't matter. So the point is that we've computed the p-adic, the explicit reciprocity law, just as the constant term of a p-adic Eisenstein series, of an ordinary Eisenstein series, and that is a p-adic L function. So the basic idea, as I said, for this construction, and the construction that Marco will explain, is that we have W and Y, 2 Shimura varieties. The Galois representation V of interest shows up in the cohomology of W, and we get extensions by looking at relative cohomology, by pull back and push forward of a class, some explicit, simple, degenerate class inside the cohomology of Y, coming, say, from an Eisenstein series or a theta series or some other, particularly simple automorphic form. And then by varying those automorphic forms, the simple automorphic forms, we hope to get an Eisenstein series. This recovers, this construction actually recovers lots of the known Euler systems. So the sketch that I gave recovers the Euler system for the ZP of 1, the cyclotomic units. If you replace the cusps with CM points, then you can recover the Euler system of elliptic units, for the Euler system for the imaginary quadratic field. If you take W to be 1 modular curve sitting inside a product of 2 modular curves, and you take 2 Eisenstein classes on the 2 modular curves, you can recover Kato's Euler system and his explicit reciprocity law. You can generalize this if you take an Eisenstein series and a CM family instead. And so you can get an Euler system for a modular form over imaginary quadratic field. That's something Marco might talk about. That's new. If you take W to be the Shimura variety for H and Y to be the Shimura variety for group G, and you take G to be GSP4, this, so you get the Ziegel threefold, and H to be GL2 cross GL2, so you get product of two modular curves. Then you can get now you take an Eisenstein series, a Ziegel-Eisenstein series on GSP Ziegel threefold, you can get an Euler system for the adjoint of a modular form. If you take G to be a unitary group and H to be a subunitary group, you can get an Euler system for unitary groups, very generally, or at least over imaginary quadratic fields. That gives you an infinite class of new Euler systems where the dimension is varying. If you take G to be GSP4 and H again to be the embedded product of two modular curves, but now you take a Klingen-Eisenstein series on the Ziegel threefold. So there's a modular form that's connected to that, and now you take two modular forms on the GL2s, then you can actually get an Euler system for a triple product. That's ongoing work by one of my graduate students, Fernando Treyes Suarez. And there are other situations, but I think I should stop there. So thank you. And again, thank the organizers for allowing me to give this talk by Zoom. I'm sorry I couldn't be there. I can't hear the audience if there are questions.
I am trying to coordinate. If there are questions, I will pass the mic around.
Me? I was almost sleeping. I am here, but so you just created most of Euler systems by this method using the explicit subvariety or something. What the entire, picture of this?
I think that's something that we don't fully understand the limitations of this. There are some naive limitations looking at just the way I've described things, where if you go back, there's kind of this codimension one picture here, that the cohomology of interest here is living in HD minus one of W, and then you need your sort of degenerate class to be in the HD of the larger variety. And so if these are all both kind of coming from holomorphic things, then you need a codimension one kind of, generally you'll need a codimension one condition for the sub-Shimura variety, which is very restrictive. And so again, if you just stick to that, then it eliminates passing to totally real fields. I don't know if this is a real limitation or if it's just a limitation of my imagination. So I think that's something we're still investigating.
Okay. I don't know why.
There's also possibilities to mix this up with the recent results or work on anti-cyclotomic Euler systems to work in other generalizations too. So yeah, so there's still things to sort of boundaries to be probed here.
I see. Yeah. Okay, thank you.
Hi, Chris. I just wanted to make a comment about the construction that you explained for the cyclotomic units using.
Yes.
So in the picture, there are these ordinary Eisenstein series and so critical Eisenstein series that show.
Yes.
And so in my work using these Eisenstein congruences, the same thing is happening.
Aha.
And I
right.
find that very interesting. Actually.
Yes, one of the things I would love to understand, and this is to maybe also reply to Hida, would be the connection between this and these constructions that Eric has been making. Yeah. So yeah. So
and this is explicitly in the explicit reciprocity law that.
Yeah. In both cases, in your case too, it also comes up in the explicit reciprocity law, right? Yeah. 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 I think
we can discuss about this one.
Yeah. Yeah. I'm sorry. Yeah. Someday we'll be in the same place.
These examples are all examples coming from GGP. So I think it is quite curious. All the examples.
Yes.
these are examples coming from GGP.
Yeah, they are all examples coming from GGP. GGP, where you know, okay, maybe you put an Eisenstein series instead of a cusp form somewhere or something. You're right. Well, again, I don't know if this is a limitation of the method or a limitation of my imagination. But as I said, I'm kind of governed by the L functions formulas, and the L function formulas I know are mostly GGP. But certainly the sort of multiplicity one picture that one gets from GGP is very, very helpful at various stages. And so the proof of the norm relations for higher dimensional things, you don't do it so hands-on. I mean, I prefer to use some of kind of multiplicity one local representation theory results. But I know that Shilin Lai is going to talk a little bit about similar kinds of things. So if not GGP, then some sort of spherical variety picture is probably at least the best context to explore these. But whether that's a limitation or not, I don't know.
All right, anybody else? If not, let's thank this again.
Thank you. Yeah.
Thanks very much, Chris.
And thanks. And thank the audience for its patience in the evening here. So have a good evening.